Yes, I'm ready. Okay. Thank you for introducing me. So, here is Giacomo Acitelli from Sapienza University of Rome, and I present our work about business process execution as a service, leveraging automated planning for frame autonomy in AI-Augmented business process management system. So let me start with some context. What are AI-Augmented business process management system? Actually, they are process information system empowered with trustworthy AI capabilities that reason and act within a set of constraints with the goal of continuously adapting and improving. So a fundamental component of this system is the process frame. Indeed, in this vision, we don't want to provide anymore the system, the exact procedure we want to execute, but instead we want to provide it the goal we want to achieve and the boundaries within it is allowed to act. So the process frame represents a set of constraints that the system must adhere to. And of course, with the process frame, we are interested in the frame autonomy, that is the ability of the system to handle multiple and possible conflicting constraints. And among them, there might be also a partial process execution that needs to be completed, even if it means at a certain points violating the constraints of the process frame. So now, how can we compute this optimal process continuation? Actually, we provided a formalization of the frame autonomy problem as a problem over deterministic finite state automata, so as a problem of theoretic manipulation over this automata. The general approach is the following one. You start from the frame, that is a set of both procedural and declarative constraints. You translate them to automata, and you augment them with special transition in order to, let's say, to capture the result of performing violation and/or recovery strategies. And at this point, the frame autonomy problem becomes the problem of finding actually a sequence of synchronous steps performing in all the automata such that at the end we reach in each automata at least one accepting state. And we did this because in this way the problem can be easily recasted as a planning problem in AI, so we can leverage planning technology in order to find an optimal continuation. And so this planning-based approach has several advantages. First of all, the correctness. Indeed, cost-optimal planners provide you the best solution by construction. Then the scalability, because you can rely on a lot of planning algorithms and also very well-known heuristics in AI. And finally, also the transparency, because both the domain, so I mean the planning model, and also the plan, so the solution, are inspectable. So now, what is the problem? I mean, what is the challenge? Of course, the techniques work, but let's say it assumes a planner inside every BPMS, and so and this in a cloud setting with hundreds of tenants is not feasible, because it means hundreds of planners that are idle most of the time, and moreover, every time you have to update the planner, you have to push that update one instance at a time. And in addition, usually tenants run small variation of the same process model, and so they keep solving planning problems that essentially are the same. And so in this context, we provide a cloud-based architecture with a centralized planner that provide planning capabilities as a service. So instead of embedding planner inside every BPMS, they invoke this shared planner allowing in addition to exploit similarities across tenants instead of solving planning problems from scratch. So in order to understand why it's important to centralized planner is important, let's consider the following scenario. So where we have a fictional SaaS platform used by e-commerce companies in order to manage their order processes, and so each company runs its own BPMS on top of it, and the process frame is composed by Patrinet, for example, that described the standard fulfillment procedure, and by a set of declarative constraints in order to capture business policies. For example, we can have a response that says that the priority order must be shipped within 1 day, and so on. And now it may happen, for example, during holiday season, that some orders deviates from its original or its standard flow, and so each one now represents a partial process execution that needs to be repaired, possibly at the minimum cost, and so the planner has to decide what to do. And notice also that even if the tenants have formally distinct process frame, they usually differ on how they name the activity names or in the order of the declarative constraints. And so basically they are the planning problem are equivalent, and a system that cannot recognize this is wasting a lot of time and effort in solving problems that maybe are already been solved. So this slide summarizes the main ideas behind our work. As I said, instead of embedding a planner inside every BPMS, we move the planner to the cloud, but we don't want only to centralize the planner, we also want to recognize when two different tenants are solving the same planning problems, and if the problems has already been solved, we directly reuse the previous result. So our work is based on three main contributions. First of all, we define planning as a service as a type service contract. Then we design a cloud-based architecture with a semantic PDDL cache. And finally, we show how our technique can be lifted to the cloud with three different usage modes. So the planning as a service can be defined as the following tuple. Yes, there are three main inputs that are the process frame, of course, the trace, that is the partial process execution that needs to be repaired, a cost function that specifies the cost of violating each constraint, and then the service performs three operations. It encodes the planning request as a planning problem in PDDL, it invokes the planner, and then he translates the planning result into a repair trace to be returned to the user. And the service must satisfy four properties. First of all, the soundness. So each trace must be valid with respect the frame. Then the cost optimality. So the service must clearly indicate the quality of the solution through an optimality certificate. Then there is the frame consistency. So the planner, the service must always use the exact version of the frame requested by the user. And finally, the tenant isolation. So a tenant must never access another tenant information. So here is the whole architecture. It is organized in three layers. On the left we have the BPMS tier. So each tenant keeps its own BPMS, where we have the frame manager that stores the frame and its version, and an adapter that is a simple client in order to communicate with the service. Then in the middle we have the planner tier, where we have the gateway that receives the planning request and the request queue that allow the system to scale efficiently when they receive many requests at the same time. And then we have the encoder that translates the planning request into a planning problem in PDDL. Anyway, before encoding the problem in PDDL, it computes a canonical representation of the frame and it checks the PDDL cache. And then we have the planner pool that contains a set of planners that works in parallel. And at the end, we have the decoder that translates the planner result into a repair trace to be returned. And on the right we have the shared infrastructure with the frame repository that contains different versions of all the process frame, and the PDDL cache that store the PDDL encoding with the relative planning solution. So now the question is, how can two different tenants share the same planning problem? The answer is through a canonical representation of the process frame. So instead of compare them based on their syntax, we compare them based on their semantic. Indeed, two process frame can be syntactically different, but semantically they represent the same planning problem. To recognize this, we compute what we call the canonical form. So first of all, we compute the synchronous product of all the automata composing the process frame, and then we minimize it through the Hopcroft minimization algorithm, and finally we rename the activity names according to a canonical order. At this point, if two process frames have the same canonical representation, it means that they are plan equivalent, and so they will produce the same solution. Once we have this canonical representation, we can cache different planning results at multiple layers. So the cache is organized indeed in three levels. The first one stores the PDDL domain. So if we find match here, we avoid rebuilding the planning domain. The second layer stores the whole planning problem. So here we can skip both the domain generation and the problem construction. And finally, the third level stores the results of the plan with its optimality certificate. And here we don't need to invoke the planner at all. We just can we can directly reuse the previous solution. So note that since the cache keys are based on this canonical representation, cache hits can also occur between different tenants, but at the same time, thanks to the label mapping, each tenant can only see its own activity names. So the service supports three usage modes. The first one is the fully autonomous mode. So here the BPMS directly execute the repair, the process continuation without human intervention. This is a good choice when we have strong optimality guarantees, and when also, of course, the domain is highly automated. Then we have the semi-autonomous mode, where the service suggests a plan, but a human needs to check it before executing. This is useful in a very sensitive domain. Let's think, for example, healthcare scenario. And finally, we have the what if analysis mode, where the user send a set of partial process execution asking for hypothetical process continuation. And here, since this partial process execution usually share the same process frame, they can reuse most of the semantic cache, and so this exploring different scenario becomes much more faster. So to conclude, of course, there are still some open challenges. First of all, moving the planner to the cloud, introduce communication latency, and then we need also stronger privacy guarantees, and finally the frame may also evolve at runtime, and so the cache has to take into account also this aspect. And as future work, we aim at implementing the full cloud prototype and experimentally evaluate cache hit race and the end-to-end latency, and we aim also at investigating stronger privacy techniques. So that's it. Thank you for your attention.
Thank you for your talk.